Hi everyone, this is Mrs. G. Today we're going to talk about the properties of rational exponents, but first I have a quick warm-up, so please pause the video. All right, so go ahead and check your work. So this warm-up is a recap of just the properties of exponents. On the next slide I have a recap slide of those properties, but here if you're multiplying terms with the same base that have exponents, we add the exponents. If you're dividing terms with the same base that have exponents, you subtract the exponents. Here's another one. Anything to the power of 0 is 1. So you'll notice that the y term disappeared altogether. And when you're raising a power to a power, you multiply the exponents. Here I did add the exponents according to the rule. Just another quick reminder, a negative exponent doesn't make your answer negative. What it does is it causes a reciprocal action to that function, and typically we don't leave negative exponents as our final answers, so we would rewrite this as 1 over x cubed. Okay, so here's just a recap of those properties. So we have the product property where we add up the exponents. Down here we have the quotient property where we subtract, raising a power to a power. And if you have a product raised to a power, each part of your product should be raised to that power. Here's that negative exponent property, the 0 property. And this, if you have the power of a quotient, each part of your quotient is raised to that power. So a really important thing to note for the product of powers and the quotient of powers, those do need to have the same base. So notice these are both base A, and then I can add up the exponents. These are both base A, and then I can subtract the exponents. So today we're going to be focusing on what are called rational exponents. So the word rational in math, it just means that it's in fractional form. So it's just an exponent that is a fraction, like you see here. So any term that has a rational exponent can actually be rewritten as a radical. So if you have x to the power of a over b, the denominator of your exponent becomes what's called the index. If you can look down here, you can see the different parts of a radical. The index of your radical. This is the radical symbol. And again, this is called the index. That's the nth root you're taking. So if the denominator is 3, you put a 3 here and you're taking the cube root of the number. And then whatever number's in the numerator of your fraction, that's still going to be the normal exponent of your expression. So you can either bring that exponent inside the radical or outside the radical. So sometimes it's easier to maybe take the nth root and then raise it to the power, or take the power first and then take the nth root. But either way, it's really important to remember that the denominator becomes the index. Another thing to point out, if the denominator is 2, the index is a 2, and that's a square root, but we don't write it. So it says if the index is not shown, it is implied to be 2. Okay, so remember, for a square root, we do not write the 2 there, but you have to know that the index is actually a 2. And then just some other vocabulary here. The inside of your radical is called a radicand. And then radicals can have coefficients, just like variables can have coefficients. So one thing today, we're not just going to be working with square roots. We will be working with cube roots, fourth roots, fifth roots, so on and so forth. So it is important to know that you can't take the even root of a negative, or there's no real number that exists. So for example, the square root of a negative number is not a real number, but you can take the odd root of a negative number. So here's a couple examples down here. We know the square root of negative 25, that's not a real number. We could say that it's 5i, but it's not real. There's no even root of a negative number. Now, you can take the cube root of a positive number. The cube root of 8 is 3, because 3 cubed is 8. But you can also take the cube root of a negative number. The cube root of negative 8 is negative 3. And that's because if you take negative 3 and cube it, you get negative 8. So it's very possible to take the odd root of a negative number. It is not possible to take the even root of a negative number. So just something to keep in mind as we're working with these different nth roots. So since we're going to be working with those rational exponents today, I want to do a quick review on how to simplify the nth root of any radical. So here in this first example, we have a square root. If you are looking to simplify a square root, you're looking for groups of 2, pairs of prime factors. So we can essentially just start dividing. I can make a factor tree. So 2 times 26 and 2 times 13. These are all prime numbers, 2 times 2 times 13. And again, since my index is a 2, it's a square root, I'm looking for pairs of numbers. So for each pair, I will put just one number out front. So it just simplifies to 2 root 13. Now for a cube root, we're going to be looking for groups of 3 to be able to simplify, or perfect cubes. So I'm going to start with my factor tree, 2 times 60, 2 times 30, 2 times 15, and then we know this is 3 times 5. So those are our prime factors. So I'm going to list them out, 2 times 2 times 2 times 3 times 5. And here, because it's a cube root, I need a group of 3 to simplify. So those 3 2's would make 8. The cube root of 8 is 2. So I get 2 times the cube root. These don't have enough in their set, so they remain inside the radicand, and I'll multiply them together. 3 times 5 is 15. All right, and then for this last one, let's do our factors again. So we have 2 times 32, 2 times 16, 2 times 8, 2 times 4, and 2 times 2. So we have 2 to the power of 6. So we have 6 powers of 2. And since it's a fifth root, we're looking for groups of 5. So 1, 2, 3, 4, 5. So it takes all 5 of those to put one out front. And you can see that I have 1 power of 2 left inside. So it's 2 times the fifth root of 2. So there's our quick review on simplifying nth root expressions. So now I'm going to ask you to pause the video and give these a try on your own. All right, go ahead and check your work here. So for part A, with your prime factors, you have 1 pair of 3s, so you get 3 times the square root of 14. For part B, you end up with 7 powers of 2. So there's one group of 4, and that leaves these behind in the radicand. So you get 2 times the 4th root of 8. And last, here's your prime factors, 2 times 3 times 3 times 3 times 3. It's a cube root, so I'm looking for a group of 3. And then you have the 2 times 3 left over in the radicand. Okay, so now we're going to start working with these rational exponents. So first we're going to practice rewriting them as radicals. Then we're going to simplify. So when I have 25 to the 1/2, remember this denominator becomes the index of my square root, or of my radical. Now, since this index is 2, we're not actually going to write it. It's implied. So this just means square root of 25. And we know that the square root of 25 is just 5. So we were able to rewrite it and then simplify. Okay, let's look at this next one. So we have 8 to the power of 2/3. So there's 2 different ways I can write this. Either way, because the denominator is a 3, it's a cube root. So I could do the cube root of 8 squared, which would give me the cube root of 64, and then I can simplify from there. Or I can write it like this. I could take the cube root of 8 and then I can square it. Either way, we'll get the same answer. But here, I know that the cube root of 8 is 2. So I can simplify that first, and then I can just square my answer to get 4. So either way, I mean, we will get the same answer. Here we would get the cube root of 64. So if you start factoring that down, we know that it's 4 times 4 times 4, which gives you the same answer. But again, sometimes it's easier to take the cube root first and then square your answer. So when you're rewriting, you could either rewrite it like this or like this. Okay, let's give this next one a try. Here I have 2 to the power of 4/5. So that means I have the 5th root of 2 to the 4th. So in this case, I know that I would need a group of 5 to be able to simplify this 5th root. But here I see that I only have 4 powers of 2. So I'm 1 power short. So this one I actually can't simplify at all. So I'm just going to rewrite this as the 5th root of 16, because 2 to the power of 4 is 16. And for this last one, here we have 3 to the power of 5/3. So it's going to be a cube root of 3 to the 5th. So maybe instead of actually figuring out what 3 to the 5th is, since I'm going to want to simplify it, I'm just going to expand it like this. It just means 3 times 3 times 3 times 3 times 3. I know I'm looking for a group of 3 to simplify. So there's 1. So that gives me 3 on the outside. And then what I have left in my radicand is this 3 times 3, which is 9. So I rewrote it. And instead of actually finding 3 to the power of 5, which is 243, I just kept it out in this expanded form, allowing me to simplify. Okay, so at this time I'm going to ask you to pause the video and give these a try on your own. All right, go ahead and check your work here. So for part A, the rewrite will be the cube root of 27 to the power of 1, so it just stays 27. And it turns out that 27 is a perfect cube. The cube root of 27 is just 3. This is definitely a good number to know and recognize. You'll see it a lot. So when you see 27, you should think it's a perfect cube. For this one, I see that the denominator here is a 2, so that means this just turns into square root of 3. Can't simplify it, so we leave it as is. For part C, this one, I think it's easiest if you actually write it like this. So my denominator of 2 makes it a square root, and then you can actually take the square root of 16 and then cube your answer. And we know that 16 is a perfect square, so the square root of 16 is 4, and then 4 cubed is 64. Or you can rewrite it like this, the square root of 16 cubed, which is 4,096, which also happens to be a perfect square. It's 64 squared. So either way, you get the same answer. And then for part D, your denominator is 4, so it becomes the 4th root of 16, which is actually a perfect 4th. 16 is 2 to the power of 4. So if you do your factors, you'll see you have one group of 4, so it simplifies to just 2. Okay, so now we're going to do the opposite. We're going to take a radical expression and rewrite it to have rational exponents. So this will just be a quick example. So first you're going to start with whatever the radicand is, and that becomes the base. And then you're going to look for an exponent. Here I see no exponent, so I could call the numerator 1. And remember, the index becomes the denominator of your rational exponent. If you'd like, you could rewrite this a little differently. Like we know that 4 can be rewritten as 2 squared, so that could actually become 2 to the 2/3. But either way, these two expressions mean the same thing. But what's important is that you would be able to turn a radical into a rational expression term. Let's look at this next one. The base is going to be x. I can see that my index is 5, so that becomes my denominator, and my numerator becomes 3, so 3 over 5. And last, square root of 7. Remember, if you have a square root, the index is a 2, so 7 to the 1/2, and that's it. So again, sometimes it will be advantageous for us to be able to rewrite in this way. Sometimes we're going to want to take this type of expression and write it as a radical, so it just depends on the problem. All right, so now we're going to move on to the properties of rational exponents. And you might notice that the properties of rational exponents are the same as the properties of any other exponent. So just because your exponents are fractions doesn't mean any of your rules change. If you're multiplying terms, you add the exponents. If you're dividing terms, you subtract the exponents. If you're raising a power to a power, you multiply the exponents. So we're essentially just using those same properties that we showed on the previous slide, but now we're doing those properties with rational exponents. So again, sometimes when you're adding or subtracting, you may have to change your fractions to make a common denominator, but other than that, it's exactly what we were doing before. All right, let's give some of these a try. We're going to use our properties to simplify each expression, and we're going to make sure that none of our answers have negative exponents. That's kind of a general rule of thumb with these. It's okay if in intermediate steps you have negative exponents, but for our final answer, we're going to want to get rid of those, and I'll show you how to do that. So for this first one, I see that I'm multiplying two terms. They are both base 7, so I know that I'm going to use my property to add the exponents. So I have 7 to the power of 1/2 plus 1/4. Now here I can see that my denominators are not the same, so I'm going to need to multiply this fraction by 2 over 2. So this becomes 7 to the power of 2 over 4 plus 1 over 4, and now I can add those up. So 7 to the power of 3 over 4. And that will be my final answer. Okay, let's look at this next one. Here, one thing really important to notice, these do not have the same base. I cannot multiply these two terms because the bases are not the same. But what I can do is I can use my power property, and I can multiply each of my individual exponents by 2. So I have 6 to the power of 1/2 times 2 times 4 to the power of 1/3 times 2. So I have 6 to the power of, well, 2 over 2 is just 1. And then times 4 to the power of 2/3. Now I know this looks a little bit strange, but this is our final answer. Sometimes you'll also just see it written like this, 6 times 4 to the 2/3. So a really common mistake that I see is people want to multiply when they can't. We cannot multiply these two bases because this term has an exponent and the bases don't match. So this, again, this is as much as you can do, and it is considered fully simplified. Even if it doesn't look like it, it is. Now if you look at this last example, I am dividing two terms. They're both base 5. So here I could use my quotient property, and I know that I'm going to subtract my exponents. But if you look, you might be thinking, well, what's the exponent of your numerator? Well, if you don't see an exponent, we know it's a 1. So I would say 5 to the power of 1 minus 1/3. I'm subtracting the exponents. Now here I'm going to rewrite 1 as 3/3, so the denominators are the same. And 3/3 minus 1/3 is 2/3. So there you go. All right, here I have a couple for you to try on your own, so please pause the video. All right, look at, check your answers real quick. So here the bases are the same, so I can use my product property and I can add up the exponents. I do need to rewrite 1/3 as 2/6, so I can add up the two exponents. And we get 13 to the 3/6, which is 13 to the 1/2. So if you have a fraction that can be simplified, we should do that. For part B, the bases are not the same. I cannot multiply these terms, but I can use my power property and multiply each exponent by 5, which I did here. So we're left with 5 times 8 to the power of 5/4. And no, you cannot simplify this any further. This would be my final answer if I'm leaving it with rational exponents. And then last, here I'm using my quotient property because I have the same base. So I'm going to subtract the exponents, 1 minus 1/9. So 9/9 minus 1/9 is 8/9. So I have 8 to the power of 8/9. Okay, let's try a couple more together. So for part A, you might notice again, I do not have the same base. So I can't multiply them as is, but you might notice something. They have the same exponent. So when I see this, I know that I can actually rewrite this. I'm going to rewrite this as 4 times 3 to the power of 5, right? Because I know that if I were to expand this out, it'd be 4 to the power of 5 times 3 to the power of 5. Now, then I'm going to take all of that and raise it to the power of negative 1/5. So this does not disappear. I'm simply rewriting this. I'm using my power property kind of backwards. So now that I've written it like this, I am able to multiply the 4 and the 3. So it becomes 12 to the power of 5 to the power of negative 1/5. And then here I'm going to multiply my exponents together. 5 times negative 1/5 is negative 1. Okay, so now here's an example where I have a negative exponent. We would not want to leave our final answer like this. So any term that has a negative exponent simply flips from the numerator to the denominator, or if it's in the denominator, it would flip to the numerator. So it causes a reciprocal action to happen. So instead of leaving my answer as 12 to the power of negative 1, it just becomes 1 over 12. And as soon as I flip the term, the negative part of the exponent disappears. So this would be my final answer. So again, we would not want to leave our final answer with that negative exponent. Okay, here, let's try one more together. Again, I notice that while my bases are not the same, so I can't use my quotient rule yet, the exponents are the same. So I can rewrite this as 42 over 6 to the 1/3, and then all of that still squared, because again, if I went backwards, this would be 42 to the 1/3 over 6 to the 1/3. Now I can use my power property. I'm going to multiply 1/3 and 2, and in that same step, I'm going to divide these two numbers. So 42 divided by 6 is 7. And then again, I'm going to multiply with the 1/3 and the 2 to get 2/3. So 7 to the power of 2/3. So if your bases aren't the same, but your exponents are, look to rewrite it using that power property, and then simplify the numbers that are within. Okay, here's the last for you to try on your own, so please pause the video. All right, go ahead and check your work here. So just like in the last example, we have terms that have different bases but the same exponent. So I'm going to rewrite it like this, and then I can multiply the 12 and the 9, and then I can use my power property here. And then remember, if you have a negative exponent, please flip that term, and then the exponent becomes positive. Same idea here. I'm going to rewrite this expression like this, allowing me to actually divide 56 and 8, and then I can use my power property to get 7 to the power of 3 over 4. All right, that is all for today's video. Thank you so much for watching.